All right, well, let's get started then. Thanks so much for coming. Really appreciate you all joining. It's a packed room. That's pretty cool. So my name is John. I work at Microsoft, and I work on the FHIR Server for Azure and the Azure API for FHIR. We're going to be talking about supporting a different kind of database in our code base, relational databases. So we're going to be talking about SQL and tables and index design, generating SQL and all that fun stuff. That's fun for me. I hope you guys will enjoy it too. So this actually was originally going to be a different talk. So note, it's actually on a different topic than what's printed out in the booklets. But let's get right to it. We're going to be talking about, trade-offs. In databases, there is no silver bullet. So we're going to take you through the journey that we went through when we designed this thing, looking at different options and sort of what we picked. But we know that nothing is perfect, and so I'm interested in sort of sharing what we did in hopes that we get some good questions from you, suggestions, and good discussion afterwards. So don't hold back on the questions, and then afterwards we're going to be hanging out at our booth, and so please come and talk to us. So the outline of this talk, I'm going to give just a brief introduction on what the FHIR Server for Azure is, why we're doing this, what the purpose of this different database type is, a quick overview of FHIR Search, because that's very fundamental to what we're building, and then sort of our table and index design, sort of what our data model looks like. I'm going to show you a demo of some queries, and then how we built this thing. So the code, I might not show you the code, but just sort of at a high level how things work and how we thought about it. And then our roadmap. So we've been at this specific project, so supporting Azure SQL for a couple of months now. The ink really hasn't dried yet. We had a pull request coming in for a significant portion of what I'm going to show last night. So there's more to come. So it's very much an active project. So let's get going. So the FHIR Server for Azure is Microsoft's open source FHIR Server implementation. And it is the same code that powers our managed FHIR Server offering in Azure. And that is called the Azure API for FHIR. So it's exactly the same code. We just have a very thin sort of hosting shim to run it in our clusters when we run it in Azure. But basically, you can see exactly what we run there, and we welcome contributions and all that sort of stuff. It's written in C# on .NET Core, and it builds on the excellent FHIR libraries published by our friends at FHIRly. We were really grateful for their great work. And it is designed right from the beginning to be pluggable and extensible. So it's cross-platform, supports different logging providers, different audit logging solutions, different identity providers, and different data stores, different persistence providers. And so that last part is really what we're going to get to here. So we started off with Cosmos DB, which is Azure's NoSQL data store solution that is highly scalable, super fast, and a managed database offering, which is really quite appealing. So why are we doing this then with all those virtues? So the FHIR data model, as you probably know, is really fundamentally it's a graph, and so it's not so much about the individual resources. It's really about the interconnection of these different resources. And we were hearing from customers that there are important parts of the FHIR RESTful spec that we didn't support, and supporting them well on our data store choice was a little bit challenging. So the graph sort of, these graph queries that you can do, or graph-like queries that really are about the relationships, so these are things like change searches, reverse include, and that sort of thing. We wanted to be able to support them efficiently at scale. And then the other thing was sort of transactions over a set of resources. Again, sort of a graph of resources. So in FHIR, there's the concept of transactions, which is a bundle of operations that basically all get committed or rolled back in one go. So if you step back and you think about this, well, this is really fundamentally about joins and transactions. Those are things that relational databases, like this is its bread and butter. It's been doing this for decades. It's really good at it. So we took a closer look at it. And we know now that relational databases and the technologies have really evolved a lot. And cloud offerings like Azure SQL Hyperscale now sort of take the scalability of relational databases to entirely new heights. So definitely something to look at. We did a couple of prototypes, and we said, okay, let's go do this thing. The goals of our project were to enable FHIR transactions, to support search parameter chaining. So there's an example here. Can't see my mouse. Can you see my mouse? Yeah. So where you're searching over encounters, but you might be interested in filtering those encounters by the practitioner that was involved, so some attribute on related data. And then things like include and reverse include search parameters, where you're including data from related resources in a search result set. So the goals then for our service were to support those operations. What we are building is a transactional FHIR service. We want to support these transactional CRUD operations with search. This is not to be confused with SQL on FHIR. So there was an excellent talk yesterday by the Google team on SQL on FHIR and protobuf and so on. That's more in the data warehousing and analytics side of things. So this is sort of a complementary technology to what we're building here, which is sort of supporting the core FHIR capabilities around versioning and transactions and search and supporting the standard. So what we want from this is really good scalability. So we started off with Cosmos DB, which gives you outstanding scalability. We want that as well with SQL. We want efficient and predictable search performance. So as we'll talk about, it's really all about search. And particularly what we want is really good performance within searches that are scoped within a single compartment, right? So a single patient's data, a single practitioner's data. And that's different from like sort of data warehouse style, aggregations over your whole data set. So that's sort of the scenario that we prioritize. And as a general principle, we want to minimize chattiness between our FHIR server and the database. And we want to support efficient bulk ingestion of data. So this is about loading up a FHIR server with as much data as possible in a short amount of time. So these are sort of the high-level goals. Not all of these we've implemented, so we don't have the transaction support yet across multiple resources, but that's stuff that's coming in our roadmap. So for something like this, it's really all about search performance. So this is how you query data against the FHIR data store. It's also used in conditional updates and within transactions to refer to other resources. It can be done in terms of a search expression. So really nailing that efficiently is what this project is all about. So let's just give a little overview of what FHIR search really means. So here's a sample patient resource. And so it has, it has a type here, it has an ID, and then has an identifier, or it has two identifiers in this case. So these are sort of like identifiers in the business domain rather than the physical ID of the document in the FHIR server. So this is a Cynthia-generated patient, or sort of a pruned one. So this is its Cynthia ID. This is the person's social security number. Its name, it has a gender, it has a birth date, so sort of standard stuff. So when you put this to a FHIR server, you do the put RESTful operation. What we do is we run a set of extractors based on the search parameters that are defined on a type. So the search parameters defined on a type define what attributes you're able to search for against a particular resource type. So each search parameter has a type, and it has what's called the FHIR path expression. And so that expression is evaluated against the resource as it comes in, and it yields a set of values. And so you can sort of see here from that resource, if we run those extractors against this resource, you get something like this. So you get a few dates, so the last updated time, there's the birth date. And so for dates, you notice that there's actually a range. So all dates in a FHIR server are stored as ranges. So depending on the precision that's specified. So the birth date really is, it's that whole day that the person was born. Whereas the last updated time is more precise. Then you have token search parameters. So these are sort of coded values. So they can be medical codes, or in this case, these are things like whether the person is deceased, their gender, in this case, male, and then their identifiers are stored or they are extracted as token search parameters. And so notice for this resource here, even the simplest one, there are 2 identifiers that are extracted. So there are 2 unique, or probably unique, ways of identifying this patient resource through a search expression. And then there are strings. So strings are pretty straightforward. So the rules for a FHIR server are that you extract the family name, the given name, and then the name search parameter can be any of those. And there are plenty of other types. So there are references, URIs, and so on. This just gives you an example sort of what this stuff looks like. So that's when we ingest it. So these are the possible search values. And then you can write search expressions that look a little bit like this. So you type this into your URI box, and the FHIR server then goes and evaluates what this expression is and matches it against the data that's stored in the database. And so these examples here would all match this resource. So the birth date was in 1998. This is their social security identifier. So we are doing a search over the identifier search parameter. We're specifying the system and the code, and they're separated by this pipe here. We would also find them by their family name or by their gender, right? So these wouldn't be the only results that would come back, right? But this resource would be in that result set. So that's sort of what we are optimizing for here, is to be able to serve these requests efficiently. So let's get into database tables. Yes, question?
So that approach that you use on URI, it's a standard FHIR API spec search approach, right?
Yep.
So there's nothing kind of...
There's nothing yeah, all we're trying to do here is to support the implement the FHIR spec.
Right.
Yeah. Yeah. So let's get to storing this information in the database. So the FHIR resource is, there's a JSON document, right? But really, if you need to be able to query over these search parameters, really what we're interested in storing for the purposes of those searches is those extracted search parameter values. So we kind of organize our tables around those values. So one thing that might be surprising is that there is no patient table or observation table or medication request table. Instead, we group things by search parameter type. And we put them in these tables that get to be pretty large. So they look something like this. So this is sort of like a first cut, like how you might kind of go about this. So first and foremost, you have a resource table. And in there, we store a compressed version of the raw JSON or XML or whatever resource that you have in there. And we store a couple of extra attributes along with it. So we store the type, so it's patient. Here's the ID that was passed in or generated by the server. And then notice that there's a version here, right? So assuming this is the same ID here, FHIR servers can optionally store the whole history trail of a resource, right? So they, as you update it, you actually don't do a mutation. You add a new version and you preserve the previous version. So we've got to keep track of that. And then we store whether it's deleted or not. So a delete is actually kind of a soft delete, and we store that as a version. So you can actually get the previous versions even after you delete it. And then you might have a table that looks something like this for storing the token search parameters. So this is where the identifiers went, and then if you like the gender and whether they're deceased, they would all end up in a table that looks maybe something like this here, right? So you're storing essentially this patient, with this type, with this ID and this version, and what the name of the search parameter is. So this is identifier in this case, the social security number, and then the code is actually that's their social security number. And then so we're preserving the history in this case, right? So it will be possible to retrieve the search parameter actually to match searches against historical values. It isn't necessary in most cases. There is some new stuff in R4 where you can have references to specific versions of a resource. And so keeping this stuff around is actually kind of helpful. So now you can, question?
Does that mean that you have other tables for
Yeah.
search parameters?
Yeah, exactly. Yeah, so we have tables that look like this for dates. We have them for strings. We have them for URIs, for references, numbers, quantities, that sort of thing.
And then it would be those other columns that are different.
Exactly. Yeah. So rather than having it all in one, and columns that are nullable and sort of this wide table, we have tables that are specific to each sort of data type that it's storing. Question, Mac?
When you have the repeat there under the token searching parameter, is that on purpose that they're repeating it, or is that because I would expect the version to be different between there and
So
the second row?
So these are two. Okay. Yeah. This is a. What am I doing? Yeah, I meant to. Sorry. Yeah. Thank you. Yeah. Yeah. I will cut you the $2.56 check. Yeah, bug in the slide. Sorry. I promise if I ran this, it would do a better job than my copy and pasting. Another question, mine?
Is there a limit on the versions, the number of versions that the system?
No, there's no limit. Yeah.
So when you refer to data types, are these all the data types that FHIR Spec supports? Like all the data types which are?
Yeah, so-
Like simple ones, there are complex ones, that's what.
Yeah, so they all kind of normalize to different search parameter types. So like token, for instance, is responsible for, a number of different types can be represented as a token. The same thing for quantity, for number, and so on. So all these different types in the FHIR spec, they all sort of funnel down to 8 or so.
Like person name, what kind of type, right?
Yep. So that'll be represented as a
Separate table, right?
no. So that ends up being a string search parameter. Yeah. So we have extractors then that can take a person name and turn that into a string search parameter.
But person name itself is a complex, right? They have like multiple.
Yeah.
boxes.
Yeah, so that was sort of what I was showing, that the name search parameter can search over the first name, last name, the first name.
The properties inside that complex.
Yeah, so there are rules for taking those complex types and sort of normalizing them to, yeah.
In order to know the current version of a resource, you have to do a maximum version.
So we're going to get to that. Yeah. So this is the first take. You can slim things down a little bit here. So in databases, if you're storing the same string everywhere, it's just more data. There's more duplications and so on. So we can take a step to kind of slim things down. So we'll introduce the concept of sort of surrogate IDs in places. So rather than having strings, we'll have an agreed upon integer or small integer, or the smallest thing that we can get that can uniquely represent this. So the first thing is the resource type ID. That's an integer. When this FHIR service starts up, there can be multiple instances. They all kind of agree on okay, patient, that's going to be 82 and so on. The ID needs to be preserved, version, history. So this here is sort of addresses your question. So we end up basically, when we ingest, we figure out if this is the latest or not, right? And so there's only going to be one of these that are going to be as history. And then the resource surrogate ID. So this represents a unique versioned instance of a resource. So that ID then can be used in the search parameter tables along with the search parameter ID, which is turned into a number instead of a string and so on. So things get more compact. We go a little bit further. The system ID, so there's typically only a very limited set of systems that will be in a FHIR server. Things like units, there's only probably on the order of 40 different units that will be there. So there are a lot of opportunities to kind of slim things down. And you could go a lot further with this. We sort of drew the line where bulk import capabilities would be compromised, but it's sort of it's a line as to how far you would to normalize. Yeah.
Sorry, if you're maintaining the versions, and I'm searching for a patient, I don't know which version that particular parameter is in. So is it going to search for all the versions to find out the patient?
So I'll answer that question in a second. When you do a search, it is by default on the most recent version of a resource. So you're basically looking at the database as it is. but you can do history searches where you can retrieve those, the previous values. But normally you can't specify all the search parameters for those. Yeah. So that's sort of how the tables look like, right? And we have that for all the different table types. Then it gets to indexes. So obviously the ingredients for it to be successful at SQL are you have to have good tables, you have to have good indexes, and you have to write good SQL. So our index sort of strategy here is sort of the clustered index is going to be based on this is for the search parameter tables, the resource surrogate ID and the search parameter ID. And so what that allows is that we're able to quickly locate, we're able to do a seek to get a particular resource at that version and evaluate a particular search parameter. And that's going to be important when we're doing sort of inner loop, or we want to be able to do inner loop joins on relatively small data sets, such as compartment searches. So the ability to sort of locate records really quickly will work with this approach. And then for each of these tables, we'll have one, sometimes more, non-clustered indexes. And so these are for basically searching by the interesting attributes. So this might be, for string, it would be based on like the string value. For quantity, it would be on the numeric quantity. In the case of a token, it is the search parameter ID and then the code and the system ID, so that you actually don't have to specify the system when you search. You might, if you wanted to, flip these, but then in the cases where you have you're just specifying the code, not the system, then it wouldn't perform really well. But the key insight here is that what we do is we store, this is a filtered non-clustered index. So it's only going to include results that, or it's only going to include the most recent version of a resource in this index. So we have these indexes across all of our search parameter tables, and they end up sort of getting, they just naturally contain only the resources that are most current for the search. But they remain in the main table, right? So the table still contains the historical values. When we go and update a resource, we mark it as history, which then ends up excluding it from those non-clustered indexes. So it's sort of a way of like, the growth of the database, of course, can continue to grow, but as the versions of resources increase, generally your search performance here is not compromised. A few other considerations. So composite searches are very common and very useful in a FHIR service. So you can do things like, where you specify a search that is over two other search parameters in a sense, right? And you separate them by this $ here. So this is something where this, the systolic blood pressure value is greater than 140. So this means that, both of those must be true within a resource for this to match. And so you have a couple of approaches here that you could take. One would be to sort of join these values together if you had some sort of correlating identifier. Or you could create dedicated tables for all these different search parameter types. And we chose the second option. So these composite searches are really useful and really common. And they could also end up being not very selective. So in SQL, for good search performance, you generally want your queries to be as selective as possible. If you were to do a join between the token and the quantity tables here, this result here, there's going to be a whole lot of blood pressure results here that you end up having to join in together. And we can save a lot of that work by basically being able to do an efficient seek to exactly this search parameter. So I'm speaking a little bit abstractly here, but we kind of optimize for this scenario. This doesn't mean that we have an explosion of all combinations of different types. We looked at the STU3 and R4 spec. We looked at the unique combinations of composite search parameter types. We created tables for those. And if someone goes and creates custom search parameters that have a combination that we don't support, well, you can open a bug on us in GitHub, and we'll get that implemented. So it's actually the way that it's implemented. There's not a whole lot of work, so we can reuse the code that goes and does the insert and the search and so on. So a little bit more work, but it was worth it. I'm running a bit short on time. Something on numeric ranges. So quantity and number search parameters. These are typically just a single value that it's extracted from a FHIR resource, but they actually can be ranges. So they can have high and low values. And then your search is actually expressed in terms of implicit ranges as well. So you end up having to do this sort of intersection between these ranges. But we kind of went with this approach, right? So you have this monotonically increasing ID. And then there's a little optimization that we can do as well, where the surrogate ID can actually serve as the last updated time as well. So because we have that surrogate ID in all the search parameter tables, we can do a restriction based on the last updated time, if that's something that you're querying on, which is actually fairly common. And basically, we do a little bit of bit shifting. So we take the current time that's on the resource, we truncate it to millisecond precision, shift it over to the left, and then add in a unique sequence, which is a cyclical and generated by the database to basically make sure that it's unique. So we give you, millisecond precision and the ability to insert 80 million resources per second. I think that's enough. Not that our FHIR server can actually do that, so so that's just a small optimization that ends up allowing us to do some more efficient querying. Let's get to some demos. So what I have running here is I have our FHIR server just running on my laptop. It's connected to a SQL hyperscale database with I think 100-something thousand patients in there. I hope the Wi-Fi is cooperating. Otherwise, I have backup slides. So I'm going to run just a few queries, and we're going to look at the SQL. So I have just logging to a console here is like the actual SQL that we spit out and execute. And so we can look at it. So the first thing I want to show is just like, OK, the basic query here, we go, slash, right? So that goes and fetches everything. So the SQL here is pretty straightforward. We're just doing a select on the resource table where we're saying where it's not history and not deleted. And then we're ordering by this resource surrogate ID. And we put a top clause on there, right? So we're not pulling down the whole database. A variant of that would be just get me all the patients. So what that looks like is very similar, but we apply a criteria where the resource type ID is equal to 82, right? Which is this magically agreed upon, or not magic, but pretty straightforward, agreed upon identifier that represents patient. Okay, let's look at something that gets a little bit more interesting. So let's look for a patient by their social security number. So here, this is where we have to go, and we can't just look at the resource table. We have to go look at this token search parameter table. And we effectively do a join. And we do a join through, we use common table expressions, which are a way of sort of declaring reusable queries that can be referenced in subsequent expressions and then a final statement at the end. So what we do here is we do a query over the token search parameter. And we say, where the search parameter ID is this, and the token and the system and code are this. In a subsequent CTE here, we apply a top and an order by clause on that. And then that result then is used in the where clause. So we restrict the resources that we return based on the results from this CTE, which is based on this one. Now, these are not persisting anything to temp tables. The SQL optimizer goes and takes us and generates one statement, and it ends up being, typically as efficient, sometimes more efficient than, if you were to generate a whole bunch of joins together. And so we expand on this pattern here. The contract with these is that they project out the resource surrogate ID, right? And then this operator does a distinct on it and does an ordering. So you can see a pattern emerge here where we're doing kind of like a functional programming style, where we can basically stack these CTEs up on top of each other that do restrictions or concatenations and things like that. So let's look at another example. This one is going to be pretty similar. This is looking at all the patient's entire compartment. So we have a table, which is the compartment assignment. We look for the resource ID of the reference, right? And then we apply this, we send it through the same pipeline. Let's go with this patient's blood pressure observations. So this is going to be within the compartment. We're going to apply another criteria to that. So here we have 3 CTs. So this one is going to be the compartment. Then we're going to intersect that with their, the blood pressure observation from the token search parameter table, and then send it through the rest of the way. So the signature here is uniform. Composite, so I mentioned that we generate tables for composite search parameters. So in this case here, we're doing the search where the systolic blood pressure meets some criteria. And so there's no, let's see here, run it. So I was going to say there's no fanciness required. So there's a token quantity composite search parameter table. But we do this funny stuff here where we're unioning it all with something, and this is to account for the ranges that I was talking about before. So here we're doing where the single value is not null, so this should account for just about all the results. But then, oh yeah, there's this extra stuff here where we need to go and check whether the high value is within this particular range. But then this ends up optimizing to, typically just a small number of reads, or sometimes 0. So again, the same pattern where the surrogate resource ID is sort of passed through and filtered along the way. And so I think like this sort of makes things readable as far as SQL goes. Even for generated SQL, compare that to what your ORM produces. And you can sort of follow what's happening. If you don't mind, I'm just going to try to plow through this. We're running short on time, and I'll get back to you. Chaining, so chain search parameters. So this is a query where we're going to do observation where the patient's birth date is July 1982. And so what does that look like? So it's sort of the same pattern, but it would just sort of adapted slightly. So the projection here on the first one, here, this is where we're doing the join between the references that are stored for a resource and that are based on an ID and actually getting the resource surrogate ID that corresponds to the latest version of that resource. So there's that join there. And then we project out 2 columns. So one is the resource surrogate ID of, I think this is observations, right? And then this one is going to be of patients. And then further filtering then is done through this CTE, where we're restricting based on the surrogate ID of the patient and then applying the filter criteria here that is based on their birth date. Here actually we apply an interesting little optimization for dates that I don't have time to get into. But if you want to nerd out with me after, we can get into it. And then double hop chaining. So encounter, service provider, name is something as well. So here, it gets more complicated, right? But it sort of follows the same pattern. And in general, we can maintain, good performance through this composable approach. So here we have to account for text overflow and so on if it's outside of the range. I'm not going to go into that. No time. Okay, so that is the demo. Just want to get into a little bit how we implemented this. So the first thing we didn't use an ORM. So our philosophy here was to build the best possible implementation with full control over tables, the indexes, and the SQL that we generate. And we don't want to implement generic databases. So we are targeting Azure SQL Server here. If we go and support Postgres, we are going to build something from Postgres from scratch. All right, we'll have some building blocks that are common, of course. But the idea is that the data provider here is targeting SQL and SQL only. And the capabilities of SQL are different from Postgres. Postgres, you could use other tricks, and the calculus would be different. And then so it's more work. You lose some of the compile time stuff. So we go and generate a whole bunch of code based on the the SQL DDL files. So we can generate helpers for all the tables and having the right columns and stored procedures and that sort of stuff. So we can we don't need an ORM for this for something like this, where we have a small number of tables and we want very precise control over the kind of SQL that we emit. Principle, as I mentioned before, minimize chattiness. So when we ingest a resource, we have to send the resource and all its search parameters. We send that all in one go with a feature called table value parameters. So this is essentially sending a whole set or a whole set of rows in a stored procedure or a SQL statement. So in one go, we can sort of transactionally go and send everything that's related to this resource, so you don't have to be chatty and do a whole bunch of calls. And what we want to do is extend that to be able to an entire bundle of resources could be ingested through a similar mechanism, maintain the transactional characteristics. And what we found is that actually ingesting a whole bundle at a time can improve throughput by about 5x over making discrete calls, even with concurrency and so on, because of that page latch contention. And finally, the SQL statement generation. So this was sort of a big part of it. So if you get something like the search string in the URI, how do you turn it into this SQL that I showed you before, without going totally crazy and having to maintain the spaghetti code that keeps track of all this stuff. So the approach that we took was we took a page from compiler design, which is you have this expression tree and you do many passes over it. And each one of these passes does some little small unit of work, which is rewriting, it's looking for a particular pattern, it's doing some little transformation. It can be tested in isolation. And we do a whole bunch of these. We do 13, and that list will probably grow. So they all kind of do something to shape it into what we want. So I'll just give you a simple example here of a couple of passes that we do to take this identifier query and turn it into sort of the logical representation of our SQL query, which then we have something that ultimately does a pass over it and turns it into SQL, but doesn't require really complicated code to actually go and do that. So we represent this in an expression tree. This is kind of a way of sort of showing a tree. This maybe looks a little bit like Lisp here, but the idea is here you have an AND expression with a bunch of two nodes, and within them. So this is an AND of where the search parameter, where basically we're saying the type here is equal to patient, and the identifier. So this is the identifier search parameter has two criteria that it must meet. The system is this, and the token code is this. So that's basically, I think, understandable from what we get in. Then we do, there's a pass that ultimately turns it into something that looks like this, where we basically build something that starts to look a little bit more like what we generate. So there's a SQL root, and there's a set of these table expressions, right? So these are the parts that we end up stacking up. So there's a table expression here that has a normalized component to it where this is going to be over the token search parameter table. And here are the criteria that we have over that table. And there's a denormalized criteria where this is what we're calling denormalized, which is this is something that applies to the resource itself, so not to the search parameter table. And that's where the type is patient, right? So that's on the resource table. The next pass of that actually goes and does a little tree rewriting where it actually got shifted and promoted to the search parameter table itself. So the type is actually stored on the table, on the search parameter table as well. It's one of the columns. And so you can further restrict entries that at that before you have to go and do a join. So just sort of a small thing there. And then the next rewriting here adds another table expression where we do this top clause and the distinct and the order by and so on. And so in this form here, we can take this and just go and spit out some SQL for it. And so that code is not particularly complicated, or much less complicated than it would be if we were just starting from this expression tree and trying to maintain the state and evolve the sort of optimizations that we need to do. So that's our approach. Our roadmap, so as I said, this is all very fresh and still very much in active development. So we have implemented chaining. Reverse chaining should be coming this week. We want to do include, reverse include, like this sort of stuff. Based on this foundation, I think it'll be pretty straightforward to implement. Transactions. This is sort of the whole purpose of building this, is to be able to support transaction bundles. Sorting, which is kind of an interesting animal here. So it's easy to sort by sort of last updated, maybe date columns, but in general, like search parameters can have multiple values. The FHIR spec says that if you're ordering by one of those search parameters, it should be the smallest one. So to do that efficiently might be hard. So we have to figure that one out. Statement caching. So all these tree transformations and so on, like they could be cached and reused. So for like a similar expression, you don't need to go and do all that work. This is sort of similar to like how query plans are cached on the SQL database. So kind of complementary to that. More efficient paging. Bulk insertion, and then for high contention inserts, there are some interesting technologies that you can use, like memory optimized tables, so essentially absorb the shock of high concurrency inserts, and there you don't deal with the same sort of latch contention issues, and then those get moved off on sort of a regular schedule to persistent tables until your queries then are over sort of the in-memory tables. And the normal B-tree tables. We haven't really gone into that, but that's something that there's a pattern that might be interesting for us. And then lots and lots of performance tuning. So I didn't show you, there's one query, and you can come up with queries here that don't perform well. So like if there's lots of data involved and lots of complicated joins and so on, like you can make this thing suffer. But for like many scenarios, there's if we can rewrite the query in a way such that it's efficient, like we'll do that. And there are certain patterns that we can spot over typical FHIR data, and we can set up like filtered indexes or rewrite the queries to, instead of OR expressions, there'll be unions, things like that. And in a couple of cases, we actually need to go and put in some index hints. So like I can show you an example later. I'm out of time now, where we set up all the indexes and we rewrite the query, and if it uses the index, it'll be nice and efficient, and then it ends up doing a table scan, right? So so like it's not our first choice to have to do that. It's sort of what we will resort to if we know for sure that this is going to be the right thing to do, and it will be a disaster if it's not, because I think if you have a FHIR server with tons and tons of data, like things can run backwards if you don't have the right queries executing. So that's what I wanted to cover today. I really encourage you to try it out. So we have our open source repo. It's there. Please give us feedbacks. Please contribute. And if this stuff is interesting to you, come join us, because we're hiring. And we're looking for great engineers. And so come talk to us. I'll be hanging out at our Microsoft booth, as will the rest of the team, for the rest of the day. Thanks so much, guys.